Hi everyone and welcome to another part of complex numbers. Today we're going to be looking at the topic of quadratic equations that have imaginary roots in them. So in addition to quadratic equations, we shall also learn about how to find the roots of polynomials of a higher degree than even those of a quadratic equation. So without wasting time, let's learn something new. Alright, so this is going to be the second part. So in the second part of complex numbers. So we're looking at complex roots of equations with real coefficients. So let's begin with solving quadratic equations involving imaginary roots. So in this section, we'll learn how to solve quadratic equations whose roots are complex numbers. The complex roots of a quadratic equation, so this is an example of a quadratic equation, so it can be stated this way. As you can see, instead of the usual x values that we're used to, here we're using z, and that's because we're dealing with complex numbers. And you know that z represents a complex number. So this is how you state a quadratic equation. Can be got using the quadratic formula. So this goes by very many different names. So some people know this as the bulldozer method, but it can easily be known as the quadratic formula. So this quadratic formula is going to help us solve the numbers in this section. So let's look at an example from UNEB 1988 question 4b. We're being asked to solve z squared plus 4z plus 13. So solution. So we're going to make use of this formula. As you can see, we're just going to substitute in the values. So we have so the coefficient in front of this is 1, the coefficient here is equal to 4, and then the coefficient here is 13. So this is positive 1, and so positive 1 is the A, positive 4 is the B, and then the positive 13 is the C. But in this formula, the B has to be negated, so that's why we convert this positive 4 into a negative 4, plus or minus 4 squared, because it's a positive, minus that. So as you can see, that's how we solve it. Alright, so when we solve this, we'll get root of negative 36 in brackets. But now this has to be simplified, and it should look so, because we want to get imaginary roots. So we must convert this into a complex number. Now we can see that the negative root of negative 36 can be split this way. We know that negative 36 is the same as positive 36 times negative 1. Okay, so when we split that with two different roots, we end up having a value like that, of which, remember, in complex numbers that root negative 1 represents I, so that's going to be an I, and then root of 36 is equal to 6, so we end up having negative 4 plus or minus 6i over 2. So we're going to split the value 2 in between the two different numerator values, and we end up like that, of which 4 divided by 2 is 2 and 6 divided by 2 is 3. So end up having negative 2 plus or minus 3i. Now this is a combination of two different answers, because this means that we have the answer, so we have two different roots. So one root is negative 2 plus 3i, and the other root is negative 2 minus 3i. So hence these are the roots. Z is equal to negative 2 plus 3i or negative 2 minus 3i. Alright, let's look at another question. So we're being asked to solve 3z squared plus 6z plus 7 is equal to 0. So we're going to use the quadratic formula. So we're going to substitute in the values the same way as we did before. So we end up having that. But as you can see, also the negative 48 can also be separated and expressed as 48 times negative 1. So we end up having a value like that, of which now we can say negative 1, root negative 1 is an I. And then 48 can be simplified to become 4 root 3. So it's going to become 4 root 3. So we end up having a value like that. And then when you split the 6 in between the two different numerators, you end up having a value like that. So negative 6 divided by 6 is negative 1. And then plus or minus a 4 over 6 is the same as a 2 over 3. So that's why you end up with a value like that. So our two answers are that. So 2 root 3 over 3 is the same as 1.1547 in decimal values. So we end up having our two answers as either negative 1 plus 1.15471i or negative 1 minus 1.1547i. And hence we've solved our quadratic equation. So those are our two roots. Those are the two imaginary roots of the quadratic equation. Right, so based on the roots we have got, we can conclude that if a complex number is a root to a given equation, even its conjugate is automatically a root to the same question. And how have we seen that? We can actually see that when you look at the final answers, the difference is just that the difference between the two roots is that there is a change in the sign in front of the imaginary part. I know that this is the conjugate of that, so that makes this not true. So we can actually see that the complex conjugate is automatically a root to the same equation. So note that, because it's going to be helpful for each of the different sections. Alright, so how about when we come to an example of solving cubic and quartic equations? So we can see that all cubic equations have three roots. We may have dealt with cubic roots when we deal with higher polynomials, those that have a degree of 3. So if a cubic equation has real coefficients, either all three roots, because we know that each cubic equation will give us three roots, so there are different circumstances it can have. So either all three roots are real, or one root is real and the other two form a complex conjugate pair. So that's the case when it comes to cubic equations. So this is how cubic equations are written. We have an A, a B, a C, and a D, so written in that format. And then we can also see that all quartic equations have 4 roots. So if a quartic equation has real coefficients, either all 4 roots are real, or 2 roots are real and the other 2 form a conjugate pair, or 2 form a conjugate pair and the other 2 also form a conjugate pair. So they are written in the form that, as you can see there. So these are just this is just some knowledge you should have when it comes to cubic and quartic equations. So the most important thing to remember is just remember that when it comes to a cubic equation, you end up having 3 roots in the final answer, and then when you deal with quartic equations, the answer must have 4 roots. Alright, so let's deal with this cubic equation. We're being asked to solve that z cubed minus 5z squared plus 9z minus 5 is equal to 0. So let's solve that. Now, to solve this, we'll actually have to first find different factors that may work out in this cubic equation. So how do we do that? We're going to first let fz to be equal to z cubed minus 5z squared plus 9z minus 5. So what happens is we need to find a value or a number that actually can make this value 0. Now, when someone is trying to think of a number to put in, I actually suggest you start from the number 1. So the first number you think of is a 1. If a positive 1 does not work, you go to a negative 1. Then if a negative 1 also does not work, you go to a positive 2. And if a positive 2 does not work, you go to a negative 2. And hence you continue like that. So that's what I suggest. Now in this case, we tried out a 1 as the value of z, and we actually saw that it gave us the value 0. So therefore z is equal to 1 is a root of the equation. So 1 worked for us, or in a good way, so we ended up not needing to look at other factors. Alright, so hence z minus 1 is a factor. So when we bring this 1 to this side of to the left hand side of the cosine, we end up having z minus 1 as a factor. So how do we find the other? So we know that when we have a cubic equation, it's like a combination of this factor that has a degree of 1 multiplying a certain quadratic equation. So we only have one of the factors. So now we need to find the other factor, and now the only way we can find that other factor right now is by long division. So we're going to divide this by the z minus 1. So this is going to be long division. So in our long division here, if we get the z cubed here divided by z, the answer is z squared. Then z squared times z minus 1, we end up having z cubed minus z squared. So when we subtract those two values, we get this. So when you have negative 5z squared minus negative z squared, remember that a minus and a minus become a plus, so we end up having negative 5z squared plus z squared. Of course that will become negative 4z squared. So this and this cancel, so this comes down and then this comes down, so we end up with something like that. So how about a negative 4z squared divided by a z? The answer becomes minus 4z. So minus 4z times z minus 1, the answer ends up being negative 4z squared plus 4z, because a negative 4z times a negative 1 becomes positive 4z. So that's why we have this. So when we subtract the two, and we have so this and this will cancel because the negative 4z squared minus negative 4z squared, where this becomes a plus, the answer will be 0. So when we have 9 minus 4z, that gives us 5z. So we have 5z minus 5. All right, so when you divide this also by z, the answer becomes positive 5. So 5z divided by z is positive 5. 5 times this, we end up having 5z minus 1. And then, of course, when we subtract this, we end up having no remainder. So because we have no remainder, it means that actually this is actually truly a factor of this cubic equation. Alright, so we can actually see that this cubic equation that we have can be expressed this way. So this times this actually gives us that. So it can actually be expressed this way. So now we can see that we can either say z minus 1 is equal to 0. Of course, that will make z to be equal to 1. Or we can say that z squared minus 4z plus 5, or we can have z squared minus 4z plus 5 being equal to 0. Okay, so now we can actually find the z. So we know the z from this side. Now let's find the value of z from this quadratic equation. So that will allow us to find the two other remaining roots, because the first root now is going to be equal to z is equal to 1. So let's find the two other roots from this quadratic equation. So you remember that when we have quadratic equations, we can solve them using the quadratic formula. So let's apply the quadratic formula to this. So the difference here is, unlike the different ones, here we have the coefficient where there is a b is actually now already a negative. But remember, in the formula, we already had a negative, a minus in front of the b. So a negative 4 inserted here will actually become positive 4. So that's why we have it like that. And then here, because this is supposed to be a positive b, so we end up having the negative 4 as it is being applied there. So when you solve that, we end up with that. Right, so we end up having something like that. And then, as you can see, root of negative 1 is, so when we split the 2 between the two different numerators, 4 divided by 2 is positive 2, and then 2i divided by 2 is I. So the roots hence end up being, so we have the 1 here where z is equal to 1. Then we also have, so we have a 2 plus or minus I. So that becomes 2 plus I or 2 minus I. And hence these are the three different roots, and hence we've solved our equation. Let's look at an example from UNEB chapter 2003, question number 12b. So we have this. So we're being asked to solve this equation. So as usual, we're going to let the fz be equal to z cubed plus 1. So now, as usual, we have to try out a number to see which one rhymes and which one will actually give us 0. So when we tried positive 1, it didn't work out because the positive 1 will not give us a 0. So when we ended, because the positive 1 will actually just give us 2. So when we put a negative 1, we actually said that's what worked. So f negative 1 is 0. So actually that means therefore z is equal to negative 1 is the root of the equation. So hence z plus 1 is a factor. Alright, so by long division, we're actually going to do a long division of this. So we have this and this. As you can see, we don't have the part where the coefficients of z squared and the coefficient of z, because those coefficients are equal to 0, and that's why they actually don't appear here. But in long division, we can actually just state them to just make our work easy, just putting them as 0. So z cubed divided by z is z squared, and then z squared times that is z cubed plus z squared. So when we subtract the 2, so this and this cancel, and then 0 z squared minus z squared is negative z squared. So bring all of this down. So negative z squared divided by this, the answer is negative z. So negative z times that becomes negative z squared minus z. Then when we subtract that, we end up having z plus 1. Now the reason is a 0z minus negative z, these two signs cancel and become a plus. So you have 0z plus z, which is z plus 1. So z divided by z is 1, so we have a positive 1 there. Then 1 times z plus 1 is that. And then when we subtract this, we actually end up having no remainder. So since we have no remainder, it actually means that this truly is a factor of that equation. Okay, so we can actually see that we can express our cubic equation this way. Alright, so when we express it that way, we can see that either z is equal to -1, or we have that. Alright, so we can actually see that we can express it as either z is equal to -1, because z plus 1 is equal to 0, so z becomes -1. Or we can also see that this quadratic equation here can also be equal to 0, of which we have that. So let's solve for this quadratic equation and find the other two values of z. So when we end up having that, we can actually see that we can solve that using the quadratic formula. So applying the quadratic formula, we end up having that, and then we can actually see that we have 1 plus or minus root of -3 over 2. But the -3 is the same as 3 times -1, which can be split that way. And then we know that root of -1 is I, then that's what we end up having. So splitting the 2 in between the two different numerators, we end up having a half plus or minus root 3i over 2. So we end up finding those two other roots. So all the roots are -1, 1 over 2 plus root 3i over 2i plus a half minus root 3i over 2. And those are our roots. Alright, how about when dealing with the formation of quadratic equations given the complex roots? So now we're going to form those quadratic equations when we are given the roots. So we have seen that if a complex number is a root to a given equation, even its complex conjugate is also a root. So this is how we form the quadratic equation from the roots. So what you do is you'll have z squared minus, then brackets, then include the sum of the roots, then there is a z multiplied to that, plus the product of the roots, and equate that to 0. So that's how you form them if you know the roots. So that's the formula. So when asked to show that a given complex number is the root to a given cubic or quartic equation, we follow the following steps. So now there are different cases, because there are cases where we have a cubic or quartic equation. So form a quadratic equation using the given complex number and its conjugate as the two roots. Then use the method of long division to divide the given cubic or quartic equation by the quadratic equation formed in step 1. Then if there is no remainder, it implies that the given complex number is the root to the given cubic or quartic equation. Otherwise, it's not. So after that, you would have been able to find the other root. So let's see how this works. Let's look at a number from UNEB 2011. This is question 10a. So we're being asked to form a quadratic equation having -3 plus 4i as one of its roots. So let's see how we form this quadratic equation. So as we said, if -3 plus 4i is the root to a given equation, then even its conjugate, -3 minus 4i, is also a root. So let's first find out the sum of the roots. So the sum of the roots we get by adding the conjugate to the original complex number. So when you add the two, we get -6. And then if we find the product of the two, so the product of the two roots will end up with 9 plus 16, which will be equal to 25. Alright, so therefore the quadratic equation is, so we're going to use the same formula. So we're going to insert the values that we've just gotten. So for the sum of roots we put -6, and for the product of roots we put 25. So when you open those brackets, we end up with z squared plus 6z plus 25 is equal to 0, and hence we found the quadratic equation. Let's look at number 2 from UNEB 2002, and this was question number 13a. So being asked, find the equation whose roots are -1 plus or minus I. So here we've already been shown that actually that these two conjugates are already the roots of the quadratic equation. So here we already have been told. So you can just find the sum of the roots. So for the sum of those roots, we have the -1 plus I plus the -1 minus I. So we'll get the answer as -2. So for the product of roots, we multiply the two and we'll end up having 1 plus 1, which is equal to 2. So following the formula, the quadratic equation is, we're going to use the same formula, and then when we insert the values, we end up with this. And then finally, our final answer will be z squared plus 2z plus 2 is equal to 0. Alright, let's look at something more complex. So this is now UNEB 2002, and this was question number 3. So we're being asked to show that 2 plus I is the root of the equation 2z cubed minus 9z squared plus 14z minus 5 is equal to 0, and hence find the other roots. So how do we deal with this one? As you can already see, if 2 plus I is a root to a given equation, then even its conjugate 2 minus I is also a root. So what we know is a cubic equation is a combination of a quadratic equation times an equation with only 1 degree multiplying themselves. So what we're going to do is we're going to first find the quadratic equation here. So we're going to first find the first factor, which is the quadratic equation. So that's what we do. So let's follow the same procedure. So sum of roots is going to be equal to 4. The product of roots will be equal to 5. And then therefore the quadratic equation that we're looking for is that. So we're going to use the same formula, and then we'll end up with z squared minus 4z plus 5 being equal to 0. So now we found the first factor. So this value here is a factor to this. So how do we find the other factor to this? We find that using long division. So with long division, so insert those there. Now we have 2z cubed divided by z squared. The answer is going to be equal to 2z. So 2z times the values on the left, so we end up with that. So when we subtract this, we end up with that negative z squared plus 4z minus 5. Alright, so negative z squared divided by z squared, that answer is negative 1. So that's why we have minus 1. Minus 1 times the values on the left, we end up with that. And hence when we subtract the two values from this side, we end up with no remainder. Since there is no remainder, it means that this 2 plus I here is indeed a root of the equation 2z cubed minus 9z squared plus 14z minus 5 is equal to 0. So let's state this. So means our cubic equation can be stated as that. So with the two factors multiplying themselves. So we can now see two different parts to this. So you can actually see that we can also say that 2z minus 1 is equal to 0, of which z will be equal to a half. Now we don't need to deal with this already, because we've already found the roots that we can get from this, which will be the 2 plus I and the 2 minus I. So the third root we are looking for was z being equal to a half. Okay, so that's what we end up with there. Alright, so we can now see that the roots are 2 plus I, z is equal to 2 plus I, z is equal to 2 minus I, and z is equal to a half. So therefore the other roots are 2 minus I, of course this being the conjugate of the root that was originally given, and z is equal to a half. So it's a total of 3 different roots. Alright, let's look at another question. So this was question number 2. So show that 1 minus I is the root of the equation 4z power 4 minus 8z cubed plus 9z squared minus 2z plus 2 is equal to 0. Hence find the other root. So this is an example of a quartic equation, but it's also the same. Now a quartic equation is more like a number that has two quadratic equations multiplying themselves. So it's likely to have two quadratic equations being the two factors. So let's solve that. So you can see that 1 minus I is a root to the given equation. So even its conjugate 1 plus I is also a root. So when we find the sum of roots, we end up having 2. The product of roots is also equal to 2. And then therefore one of the quadratic equations, because we said there are going to be two different quadratic equations, one of them is going to be equal to that. So insert the value of the sum of roots and the product of roots, and we end up with z squared being equal to minus is going to be z squared minus 2z plus 2 is equal to 0. So we can see that z squared minus 2z plus 2 is a factor of our equation. So now we need to find the other factor. How do we find the other factor? By long division. So insert that there. We can see that 4z power 4 divided by z squared is equal to 4z squared. Multiply the 4z squared by the values on the left hand side, and you end up with that. So when we do a subtraction, our answers are z squared minus 8 minus 2z plus 2. So z squared divided by z squared is 1. So we end up having a 1, and the 1 times the values on the left is equal to that, and hence we are left with no remainder. So since there is no remainder, it means that this 1 minus I is actually a root of the equation. So when we're going to write the equation out, and as you can see that now we have the equation having those two different factors. Now these two different factors give us two different perspectives. We can already see that this quadratic equation here, the first one that we had derived, is the one which has these two different roots, 1 minus I and 1 plus I. So now we need to deal with this other new quadratic equation that we've actually just found to find the other value of z. So as you can see, we can already say that this is equal to 0, and therefore making z squared the subject, we end up with negative 1 over 4. So we can also see that z is going to be equal to root of negative 1 over 4. But since we're dealing with complex numbers, we know that a root of a negative 1 means something, so this can be separated that way, of which we know that a root of a negative 1 represents I, so we end up having a half I. So our roots, we have z is equal to 1 minus I, 1 plus I, then we have also z being equal to positive or negative a half of I, because we know that a root of something can have a positive or a negative answer. So this is going to be our roots. So we end up having 4 roots. So we write this as plus or negative as a simplified way of writing the two different versions of this, because we have a positive a half I and a negative a half I. So at the end, we've had 4 different roots to this equation. So question number 3, show that I is a root of the equation z power 4 minus 4z squared plus 21z squared minus 4z plus 20 is equal to 0. Hence find the other roots. So let's solve this. So you can see that if I, now this is an example of a purely imaginary root, a purely imaginary number. So that means the real part is 0. So if I is a root to a given equation, even its conjugate negative I is also a root. So the sum of roots, now here we've stated it, we've shown that the real parts are actually 0. So when we actually add the two, we get 0. Then product of roots is also like that. We can also say the answer is 1. So therefore, one of the quadratic equations is that. So we're going to insert the value of sum of roots and the value of product of roots, then we end up with that. So we end up having z squared plus 1 being equal to 0. So we can see that z squared plus 1 is a factor of the equation. So let's find the other quadratic equation. How do we do that? The other factor, we find that by long division. So we can see that z power 4 divided by z squared is z squared. Z squared times values on the left, we end up having that. As you can see that there is no other value of z cubed to subtract with this, so this shall stay as it is. So we'll have 21z squared minus z squared. So we end up having this as 20z squared, and then this stays as it is. So we end up having that. So now negative 4z cubed divided by z squared, the answer is negative 4z. Negative 4z times the values on the left ends up giving us that. As you can see, when we subtract this again, there is no value to subtract with the 20z squared, so it stays as it is. Then we have negative 4z, actually minus means plus, so we have negative 4z plus 4z, which is actually equal to 0. So we are left with 20z squared being equal to 20z plus 20. So when you have 20z squared divided by z squared, the answer is 20. Then 20 times the values on the left gives us that. So which when we subtract, we have no remainder. So since there is no remainder, it means I is actually a root of the equation. So writing the equation out, you can see that these are the two different factors. So you can see that there are two different parts to it. Now we're interested in the second quadratic equation that we've actually just derived, and we're going to find the other remaining roots from it. So from z squared minus 4z plus 20 is equal to 0, we're going to use the quadratic formula. So when you substitute in the values, you end up having that. So when you simplify, we have a root of negative 64, which we can also simplify as 64 times negative 1, of which you know that root of negative 1 is an I and root of 64 is an 8. So we end up having this. So when we split the denominator to the two different numerators, we have it simplified as that, because 4 divided by 2 is 2 and 8 divided by 2 is 4. So these are the roots that we actually find. So we know z is equal to I, z is equal to negative I, and also z is equal to 2 plus 4i or 2 minus 4i. So those are our roots. Alright, let's look at another question. So we're being asked to show that z is equal to 3 is a root of the equation z cubed minus 2z squared plus 3z, plus 2z minus 15 is equal to 0. Hence find the other roots of the equation. So we're being told that z is equal to 3. What does this mean? If z is equal to 3 is a root to a given equation, that means that z minus 3 should be a factor. That means you can just simply find one of the factors by simply taking the 3 to the other side. Now this is an example of a purely real complex number, because we can say the imaginary part is 0. That's why we don't see it appearing, so it's a purely real one. So if we want to find the first root, the first factor, it's as simple as bringing the 3 to the other side. So you can see that z minus 3 has to be a factor. So this is actually much easier. So we can actually go straight to long division to find the other quadratic equation. Alright, so this can be, now for this case we cannot do sum of roots because we may not know what the imaginary part looks like. So long division will help simplify this for us. So when we have this, z cubed divided by z is z squared times the values on the left, we end up having that. So when you do subtractions, these are the answers we end up with. Then z squared divided by z is equal to positive z. Positive z times z minus 3 is equal to z squared minus 3z. So when we subtract this, we are left with 5z minus 15. So 5z minus 15. So we have 5z divided by z is going to be equal to positive 5. 5 times z minus 3 is going to 5z minus 15. So when we subtract those, we are left with no remainder. So since there is no remainder, it means that z is equal to 3 is surely a root of the equation. So now we're going to insert the two different factors being equal to 0. Now we can find the other two unknown roots from the new quadratic equation that we've actually just found out. So we can actually see that we've said that z squared plus z plus 5 is equal to 0. Of course, using the quadratic formula, we can actually work this out. We already know the first root is z is equal to 3, so we can leave this part out. So let's deal with this. So using quadratic formula, we end up having that. So we have 19 times negative 1, of which we can see that the negative root of negative 1 represents an I. So we are left with that. So alright, so now we can see that our roots are, we have z is equal to 3, then we have z as negative a half plus or minus root 19 over 2i. So the other two roots that we're actually looking for that we didn't know are negative a half, then plus or minus root 19 over 2i. So these are the other two different roots. Alright, let's look at another question. We're being told that one root of the equation z cubed minus 6z squared plus 13z plus k is equal to 0, where k is real, is 2 plus I. Hence find the other roots of the equation and the value of k. So this is an example where we actually have some few unknowns. So how do we work this out? So we've been told that we have an unknown root. So one of the roots is 2 plus I. So how do we work this out? So we can already see that one of our roots is 2 plus I. So that means we can simply state that z is equal to 2 plus I. So since this is a root, so therefore the value of z can be equal to 2 plus I. So let's find the value of z for both of these sides. So what happens when z is squared? So we're going to deal with what happens when z is squared and when z is cubed. So that will help us find the value of k. So when z is squared, we end up having that. So when we split this into two different brackets, we end up having that as our answer, of which we know that I squared is equal to negative 1. So 4 minus 1 is 3. So we end up having z squared being equal to 3 plus 4i. So let's also find the z cubed. So z cubed is going to be obvious, z squared plus times z, of which we know what z squared is equal to. Z squared is equal to this, and then z is equal to that. So we can actually see that these are the two different, this is what we have. So when you multiply these two by the knowledge of multiplication of complex numbers, this is what we end up with. Of course, we know that I squared here means negative 1. So negative 1 times this, so it's going to have 6 minus 4, of which we'll have a 2. So we have 2 plus 11i. So now that we know what z squared and z cubed are, we can substitute them back here to find the value of k. Alright, so putting back into the cubic equation, this is the cubic equation. So we're going to substitute values. So where there is z cubed, we put this in. So where we have the z squared, we actually put in this, the 3 plus 4i, as you can see here. Then where there is the 13z, we're going to put the value of z, which we already knew, right there. Then when we solve this, we'll have that. So we end up having 10 plus k being equal to 0, and you can actually see that k is equal to negative 10. So we've actually found the value of k. So now that we found the value of k, we can actually now continue to solve to find the other roots by using long division. But now we can already see that the first root that we have is 2 plus I. So let's first find that first factor, that first quadratic equation. So the first quadratic equation can be found this. So using sum of roots is that it's going to be equal to 4. Then product of roots is going to be equal to 5. Then therefore the quadratic equation is that. So when you substitute in the value of sum of roots and product of roots, you can see that the first quadratic equation is z squared minus 4z plus 5. So now let's find the other factor using long division. So z squared minus 4z plus 5 is the factor of that equation. So let's use some long division to find the other factor. So using long division, you can see that z cubed minus, divide by z squared is equal to z. So z times the equations on the left, we end up having that. So when you do a subtraction, we end up having negative 2z squared plus 8z minus 10. So negative 2z squared divided by z squared, the answer is negative 2. Negative 2 times the values on the left, we end up having that. So when you do a subtraction, we have no remainder. So since there is no remainder, we can see that clearly 2 plus I is the root of the equation. So now that we have our equation here, we can see that the two factors multiplying themselves can be substituted in, and then we have that. So now we can look at the equation that we actually just derived, the factor we actually just derived, to find the other value of z. So we can see that if z minus 2 is equal to 0, therefore it means that z is equal to 2. So therefore the other roots are, so the roots are z is equal to 2, z is equal to 2 plus or minus I. So these are the three different roots that exist for this cubic equation. Question number 6. Given that z is equal to 2 minus I, so here we've already been given a root, is a root of the equation that where k is real. Find the other roots of the equation and the value of k. So this is as easy as the former one. We know that z is equal to 2 minus I. So therefore we can see that we can find z squared. Z squared is that. We can see that z squared shall end up being 3 minus 4 I. Then when we find z cubed will be equal to 2 minus 11 I. So putting this back in the cubic equation, we end up having that. So we've substituted the two values in, the value of z squared and the value of z cubed. Then we've also substituted in the value of z, which is 2 minus I. So when we solve those and simplify, we end up having negative 5 plus k being equal to 0, of which now we can see that k is clearly equal to 5. So now let's first find that first quadratic equation, which is the first factor of this general cubic equation that we actually have there. So we can use the knowledge that we have. So we already know that if 2 minus I is a root to the given equation, even its conjugate 2 plus I is also a root. So the sum of roots shall be equal to 4, then the product of roots shall be equal to 5. So therefore that first quadratic equation is going to be z squared minus 4z plus 5 being equal to 0. So therefore z squared minus 4z plus 5 is a factor of the equation. So by long division, to find the other factor of the same cubic equation, we can actually see that z cubed divided by z squared is z, of which z times z squared is times the values on the left, will end up having that. So when you do a subtraction, we are left with z squared minus 4z plus 5. So z squared divided by z squared is 1, so we have a positive 1. Then 1 times the values on the left, we end up with that. So we're left with no remainder. Alright, so since there is no remainder, it means that 2 minus I is a root of the equation. So we can see that when we substitute the factors in, we end up having that. So we end up having z plus 1 also being equal to 0. So therefore z is also equal to negative 1. So therefore the roots are z is equal to negative 1, and then the ones that we already knew, z is 2 plus or minus I. So these are the three different roots of the equation. Alright, so we have this other one. We're given that z plus 2i is a factor of the equation. So this is a quartic equation. Z power 4 plus 2z cubed plus 7z squared plus 8z plus 12 is equal to 0. So solve the equation. So how do we solve this? So if a z plus 2i is a factor to a given equation, then it also means that z is equal to negative 2i should actually be a root to the given equation. So now that means this is going to be a complex number that is purely imaginary. And also now that we can say that z can be equal to negative 2i, it also means that if negative 2i is a root to the given equation, then even its conjugate 2i is also a root. So some of the roots, let's first find that first quadratic equation. So in this example, we're going to have two different quadratic equations because it's a quartic equation. So we end up having the sum of roots as 0, and then the product of roots will also be equal to 4. Okay? And therefore, the quadratic equation, the first quadratic equation is going to be equal to z squared plus 4, which is equal to 0. So now to find, so we can see that z squared plus 4 is the factor of the equation. So now we're going to find the other quadratic equation from long division. So by long division, let's insert that there. So z power 4 divided by z squared is z squared. So z squared, multiplying the values on the left, we end up having that. So now we have nothing to subtract with the z cubed, so it will remain as it is. But z squared minus 4z squared is going to be equal to 3z squared. So we end up having that. So 2z cubed divided by z squared is 2z. 2z times the values on the left, we end up having that. Now there is nothing to subtract the 3z squared as it with any other, so it's preserved as it is. And then 8z minus 8z is 0, and we are only left with the 12, so we have that. So 3z squared divided by z squared is positive 3, so that's why we have a positive 3. Positive 3 times the values on the left, we are left with that. So since there is no remainder, it means that negative 2i is the root of the equation, of that quartic equation. So we can actually see that now, substituting the quartic equation with its factors, we end up having that. So now, using the new quadratic equation that we've actually found, we can use the quadratic formula to find the other values of z, to find the other two remaining roots to the equation. So when we substitute the values in, we are left with that. So we end up having root of negative 8, of which root of negative 8 is the same as 8 times negative 1, of which we know that root of negative 1 is an I. So we're left with that. So simplifying the root of 8 is the same as 2 times 4, which know that root of 4 is 2, so the 2 goes outside the root, so we're left with 2 root 2. And then negative 2 divided by 2 is actually negative 1, so that's what we actually left with. So now the 2's here cancel, so we're left with a negative plus or minus root 2i. So these are two different values of z. So we can see that these are the values of z that we get for this quartic equation, and hence we've actually solved it. Alright, so lastly, I would just encourage you to try out these numbers. They will help you get better at this section. So this is going to be number 1. So after this number 1, you can actually see that I've given you answers right there for you to be able to compare and prove that you're actually on the right track. So number 2, number 3, number 4, and number 5. So I believe after you try out these numbers, you'll be an expert in this section of complex numbers. Thank you so much for watching. Thank you so much for watching this video. Thank you for watching to the very end. I am very, very grateful. I hope this video has blessed you and that it has improved your knowledge of complex numbers. If you really enjoyed this video, or if it really helped you, feel free to leave a like on the video. And then if you're new to this channel, I encourage you to join our community by clicking on the subscribe button and then joining it, and then make sure to hit the notification bell so that every single time I upload a new video, you'll get updates on your notifications. See you in my next video.